Okay. All right. So, what do you got for me? Or are you just going to read through it again?
Yeah.
Go for it. Okay, that sounds right. Because it's the same problems as last time, but parts like B, C, and D, right?
Yeah.
Okay.
So how much Clocksky can surgery tolerate? When this operates trigger, how much Clocksky can surgery tolerate before it might experience it. And then he goes on a whole tangent.
Yes, it does. Yes, it does. So the first one was what? The one with the 3 XOR gates? Is that right?
Yeah. A lot going on. How do we determine clock skew?
How do you determine what?
Clock skew?
So typically either clock skew is given to you, or you have a circuit and you have to ask yourself how much clock skew can I take before my circuit starts to break. So which one is this?
Asking you how much to break.
Yes. All right, hi Shauna, we're just starting up with just problem 1 for homework 7. So yeah, I'm going to go ahead and draw out this diagram, same as the one we saw last office hours or from the previous homework. But 3.33. Man.
Hey, Victor.
Yep.
Is your camera working on your end?
Yes, is it not for you?
No, it's like got, no. I'm gonna try reconnecting, maybe.
Well, it's
Oh,
apparently
there it
just
goes.
recording. It's
I
good
got
now?
it.
Okay, cool.
Yep, thank you.
All right. Let's see. That's rough. Okay. So we have, this is the stuff that's in between the registers, so it's just the 3 chained XOR gates. And we're asked to figure out how much skew our circuit could tolerate. And so this is going to be partly related, or quite a bit related, to the answers we got from last homework, which are just going to be the equations that we derived, and then the final computations we got from those equations. So remember, the equations were just the setup time and hold time equations. So we had the first one. So we have the clock time has to be greater than or equal to the total times of reading out of the register, going through the combinational logic, and then being read into or waiting to be read into the next register. So that's what's going to impact our clock time. And then we also have the hold time equation. which just means that our circuitry cannot run a signal through fast enough to be faster than the hold time. So if we read out of the register in the fastest possible time and propagate through our combinational logic in the fastest possible time, that cannot be less than or equal to the hold time. And so what we're going to be doing this time is we're going to be considering skew, and we're going to be considering skew in the worst case possible. So like I mentioned last office hours, depending on the orientation of the skew, either the second clock comes later or earlier than the first clock, you actually add the skew term to one side of the equation or the other. And so it'll look something like this. Either it'll be you add skew here, or you add skew to the left-hand side. Now, for the top equation, we would rather have skew on this side, and I'll explain why. If we have skew on the right-hand side, that means that our total clock time is actually going to increase because we're adding a number on the right-hand side, and this has to be bigger than the right-hand side. So this is going to have to be a bigger number, which is bad because that means our period is longer, so our operating frequency is slower. So we can't run the circuit as fast if we add the skew on this side. If we add the skew on this side, you can think about subtracting it over there. And we get something that looks like this. We have all these terms added and then we subtract something. So what that means is that this doesn't have to be as high, which means our period is shorter, so our operating frequency can be even faster. So this is the best case scenario skew, where you subtract it here, or in other words, you add it on the left-hand side, versus if you add it here, that's the worst case skew. And that's for the clock time. Similarly, for the hold time constraint, you have to ask yourself where you want to have the skew added. So if you add the skew to the left-hand side, then that makes it harder for t-hold to still be less than the right-hand side, because we want t-hold to be small. We want it to be smaller than the right-hand side. So if we add something to it, that makes it harder for us to keep this condition in check. However, if we add the skew to the right-hand side, that makes it easier for us to maintain the condition that t-hold is less than the right-hand side, because whatever we had previously, if we just add something onto it, then this is definitely still going to be less than it. So we can tolerate. So if the skew is added onto the right-hand side, that means our t-hold can be bigger, and it'll be fine. So now we need to determine how we're supposed to place that skew in our equation, depending on the orientation of the skew. So there are two orientations. Alright, so here I've drawn the first orientation. So this is your input clock. All I've drawn here is a buffer symbol. So all that means is that the clock arrives here instantaneously, very quickly, whereas it arrives to this register at a longer time afterwards. So let's say maybe 10 picoseconds of delay, just to have some sort of estimate value. And what we're going to do is we're going to determine how that impacts our equations here. So let's ask ourselves, if this clock arrives at some time, and then the clock arrives at the second register at a later time, specifically 10 picoseconds later, we have a diagram that looks like this. Okay, so now let's ask about the clock time that we can run this at. So if we had a register being read out of here, or if we had a signal being read out of this register, propagating through the internal logic, and then being read into the second register, that's just our standard terms that we have here. We have the PCQ, propagation clock to Q, so that's reading out of the first register, the delay through the internal combination logic, the TPD, and then the setup at the time we wait at that second register to be read in. So let's just imagine that we had these times labeled on our diagram here. So let's do that. And for the moment, I'm going to ignore the fact that I have the 10 picoseconds here. I'm just going to draw these in. So the first thing I do after my clock hits is I read out of my register. So that's that first little time interval. And then maybe for the second little time interval, I have the time that it takes to go through the combinational logic. And then finally, I have a little bit more time for the setup, how long I have to be at a stable signal before the register reads me. In a standard system where both of these receive the clock at the same time, both the clocks would be identical to this first line that I've drawn, to this first clock signal. And so these three lines, they go from the very first rising edge to the second rising edge, and they take up all the time. And this is the case where TC equals those times. So my clock time that I have here, this period time, is exactly the same as all these internal timings. Now, that's the best I can do if the clocks are perfectly aligned. If they're unaligned, then this needs to fit within this region. So all I've done is I've drawn the exact same arrows, but on the second clock. Now here's a question. For this first clock, we used up all the space. We couldn't have decreased the period, because if we did, then we'd be violating our setup time. We would be going too early. How about here? Is there any wiggle room left? Because it looks like to me we got some space here we can fill up, right? So what that means is that if we skew in this direction, that benefits the clock time. So it makes it easier for us to shorten the period. So we could, if we wanted to, shorten the period to, say, however much that amount is. So let's say the entire period was 50 picoseconds. This little interval is 10. We could shorten the clock cycle time from 50 to 40, because this second register, because it's skewed off 10 seconds further in time, those 10 seconds we used at the beginning are saved here at the end. And so we can increase our cycle, we can increase our clock frequency. So all of that is saying this is the best case scenario for TC. We just found out that if we skew it in this direction, then our clock time has benefited. It's better for it. So it's better for it. So then we ask again at the beginning whether or not we should add skew to the right-hand side or the left-hand side. And so if we look on the right-hand side, that would be the worst case scenario, because we're increasing this right-hand side, and the left hand has to be bigger than it. If it's bigger, that means it's a longer period, shorter frequency. That's bad. We want to be able to run our frequency at a higher frequency. We want to be able to run our circuit. So if we add T-skew over here, that's the worst case scenario because it's a longer period. If we add it over here, which is the same thing as saying subtract it from the right-hand side, if we subtract it from the right-hand side, that means that our clock time can be smaller, so our period can be smaller, which is to say our frequency can be higher. We just said, according to our diagram, this is the best case scenario. So the skew is added to the left-hand side. Now, you can either just memorize the direction of the skew corresponding to whether or not you add the skew to the left hand or the right side, or you can kind of mentally derive it for yourself by like drawing out a rough sketch of this. So again, I'll go through one more time. We have two registers with combinational logic between, and there's a delay going from the first to the second. This receives the clock 10 picoseconds earlier than this one. And so I've drawn that on this diagram. Here we have the clock cycle that register 1 sees, and here we have the clock cycle that register 2 sees. Register 2 gets the clock cycle rising edge 10 picoseconds later. So all I did was I drew out these 3 timings on my diagram. Reading out of the register, going through the combinational logic, and waiting at the entrance of the second register to be read in. And then I drew those exact same times on the bottom diagram. What we saw is that we still had some space, some leftover space before the rising edge that we could use to shorten the period with. So what that means is instead of having maybe a 50 picosecond period, we can have, say, a 40 picosecond period. So that's better for our cycle time. Since it's better for our cycle time, we add it on this side, because if we add it on this side, same as subtracting from there. And the smaller this is, the smaller this can be, which is better. We want shorter times so we can have higher frequencies. Now, I know I talked through that for like 10 minutes straight. And that's just because I was trying to kind of pound it into your guys' heads. Do you have any questions with how I went from this diagram to the schematics to my conclusions about the equation and the placements? Because I know it can be very confusing. I had a really hard time understanding this when I first took CPU 200. So any questions? Okay, so for the moment, I'll continue on just a little bit. If you guys have questions, please let me know. So we just figured out that this specific orientation of skew is awesome for our cycle time. So we want it to be in this orientation for cycle time. Now let's ask, is it good for the hold time constraint? So what we're going to do is we can take a look at the same exact diagram, but instead of drawing the top timings, I'm going to draw the bottom timings. So instead of having TPCQ, TPD, and T-setup, I'm going to have TCCQ, TCD. So I'm going to go ahead and do that, and I'm going to go ahead and draw it on a separate little part over here. And I'll do it, I'll do it up here.
Can I ask a question when you're done?
Yeah, go for it.
So we said our final thing was sorry, it's just like really light, so I'm having trouble
Yes.
seeing it. But we said it was the normal TPCQ plus TPD plus T setup, and then we said minus T skew.
Yeah, so basically I was just saying, where do we add it? We came upon that we
Yeah.
add it to the left, and that's the same thing as saying if you were to subtract this from both sides, you'd get minus T skew on the right-hand side, which is the
Right.
best case scenario.
Okay, I was just looking at the book, and I thought it said it was added to the right side.
Depending on the skew orientation, yeah, it depends. So
Oh,
if it was-
okay. So this isn't a hard. Oh, yes. You said okay. So if the clock was like on the other side, yeah. Okay,
so
that
if the
makes.
clock came in here and there was
Yep.
a time delay going to the
Got
left,
it.
then it would be added on that side,
Oh,
absolutely.
okay. That makes way more sense. Thank you.
Yep. Okay. Now I'm explaining it with it heading in that direction, but our conclusions are going to be exactly the opposite when we head in the opposite direction. So if it's delayed this way, instead of a minus here, it'd be a plus, and it'd be the same for the whole time. We swap it. All right. So again, I'm going to ask, how does this benefit or hinder our T-hold? So I'm going to start drawing on that diagram too. Remember that the way T-hold works is you have a time after the clock edge hits, and you need to hold your signal steady for that time interval in order for the register to read it in properly. If it changes within that interval, you could get an incorrect reading. And so here's what I'm going to do. I'm going to draw T-hold. So here's the first clock, and here's the second. And so here, we've just hit our positive edge of the clock, and so we want to read in our data. This is a very, very exaggerated length of time. Typically, they're not that long. But this is just for the fact that I want to be able to fit it on the whiteboard. So say this is our hold time. Remember that hold time is how long we have to hold it after the rising edge hits in order to read into the register. And what we want to happen in order for our hold time constraint to be met is for these two terms, the time to get read out of the register from register 1 and to propagate through the logic between the two registers, this has to be longer than the hold time. Or in other words, the hold time has to be shorter. So this is what we want to happen. Now, let's think about when TCCQ and TCD start. Those are read from the first register. So what that means is, unlike how I've drawn it in the diagram, your value isn't read out of the register 1 when clock 2's clock edge hits, but rather when when the register 1's clock hits, because this is the guy that you're reading out of. So I've drawn it here, but actually, it's supposed to be aligned to this one. And so now suddenly, despite the fact that before, how I had it if they were aligned, so it starts at the same time as the second clock, if they were aligned, the TCCQ and the TCD total time was longer than T-hold. So my hold time violation, well, it wasn't violated. It was actually confirmed that we don't have a time hold violation. However, now that I have this shift between the clocks, the skew between the clocks added in, you'll notice that this moves back to the left, and now it actually falls within the interval of the hold time. So we said at the beginning, we better not change the signal in the middle of that hold time because we're not going to read in the right thing into the register. And now, because of this skew, we've suddenly made it so we have changed it during the hold time. So this is actually the worst case scenario for the skew. Remember that the worst case scenario for the skew is to add it to the left-hand side, because remember, we want this left to be less than the right. And we want it to be less than it by a lot, as much as possible. So if we add something to it, it makes it harder for it to be smaller. And again, if we're saying the current situation we're in is adding the skew on the left-hand side, that's the same thing as saying you're subtracting it from the right. So in this orientation, where the first register, kind of the input register, if you will, has the clock arrive earlier than the second register, the one that, the output register, if you will. If this clock arrives earlier than that one, you subtract the skews. If it was the other way, we would have the exact opposite conclusion. We would instead add the skews. And so that's a bit of a derivation for how you get these skews and how to determine, based off of which orientation you're in, how to either add or subtract the skews. So now that I've kind of gone through that, any other questions for me? And this is a hard topic, so this can be a hard topic to learn, so don't feel bad if you don't get it on the first or second or 15th time looking at this, because it can be pretty difficult to understand.
Yeah, so the most important part is going to be like this, so let's...
Okay, so we've just said that if we're skewed this way, we add, and if we're skewed the opposite way, we subtract. And so let's ask ourselves, in our current question, which skew orientation we're dealing with. That's the most important part for how we're going to be doing this analysis. So if we're dealing with a skew orientation this way, it's really, really good for the clock time, because it's going to be minus there. But it's really, really bad for the hold time. And if it's the opposite direction, then it's good for the hold time and bad for the cycle time. So in fact, no matter what the orientation is, it's always going to be best case for one of them and worst case for the other. So if you know one of them off the top of your head, you can always get the other one. So if we're in the best case scenario for the clock time, it's always worst for the hold time. If it's best for the hold time, it's always the worst case scenario for the cycle time. Okay, so for this question, what do they ask you to do? In part B, for 3.33.
Maybe I should just add this and see if
Or I could open up the homework myself.
So it's just asking how much clock skew can the circuit tolerate if it must operate at 2 gigahertz?
Okay, so we want this to operate at 2 gigahertz. And what we're going to do is we're going to consider the worst case scenario for the timing, because it sounded there like timing the clock time was the constraint. Specifically, they mentioned 2 gigahertz. So I'm going to focus on the worst case scenario for this top equation, the clock time equation. So remember, the worst case scenario occurs when we add the term over here, we said that skew going this way, where the clock of 1 arrives before the clock of 2, is the best case scenario for TC. We want the worst case scenario. So in this particular case, we're going to consider the skew backwards, where clock 2 receives it earlier than clock 1. And that would be adding the skew there. And so here's what we want to do. We want the frequency of our circuit to be at least 2 gigahertz. So we want it to be able to run at 2 gigahertz. What does that tell you about your cycle time? What equation could I write for the cycle time if we know the frequency is greater than or equal to 2 gigahertz?
So wouldn't we want to start off with frequency equals 1 over TC?
Yes. And then what relation should I put? Should I put less than or equal to or greater than or equal to? Yes. Whenever you have inequalities and you do reciprocals on both sides, because that's what I just did, I reciprocated both sides, I flipped the fractions, you have to flip the inequality as well. So our cycle time has to be less than or equal to some specific number. In this case, that number, I believe, will be 500 picoseconds. You can check with your calculator to verify. But this is the conclusion we've arrived at. If we want our circuit to run at least 2.0 gigahertz, at 2 gigahertz, we need to have a cycle time of less than or equal to 500 picoseconds. Is everyone all right with that?
Yes.
Okay, so here's what I'm going to ask. Based off of what we did from the last homework and what we can redo now if we need to, we already know TPCQ, TPD, T setup. That was, again, from the last homework. So whatever that value was, I think it was like 160 something, I can't remember off the top of my head. We could also recalculate it now. But whatever that value was from your last homework, I'm going to assume 160. We can then ask ourselves, well, what can our maximum skew be if we don't want to go above 500 picoseconds? Well, in this case, right, you just need to subtract 500 minus 160. You're going to get 340 picoseconds of skew. And that's the basic calculation. So for this problem, you don't really have to know which way the orientation of the skew is. You just have to consider the worst possible case, which again we mentioned would be adding the skew to the right-hand side of the clock time equation. And again, like we said, if you figure out just the normal cycle time without skew, all you have to do is figure out what the difference of your desired time is minus the time without the skew is to figure out the maximum skew you can tolerate. If we had 341 picoseconds, this would then be at 501 picosecond cycle time, which is less than 2 gigahertz frequency, if you do the reciprocal of that. And so we would not meet the desired requirements for this circuit. Now again, these are just numbers I threw out there. Well, these are correct, but the 160 is just a number I threw out there. That just depends on what the actual circuit delay is. So you'd have to go back and calculate it. I think for each XOR gate, it was like 100 picoseconds or something, maybe 50 for the question. I can't remember exactly off the top of my head, but you'd use the values for your problem to plug into those. So any question?
Was also random, or?
Well, yeah, it's random, but it depends on this. So I randomly picked 160, and I just said, let's pretend these added up to 160. And then I said, well, I know this for sure, because we know it has to run at 2 gigahertz. So I know the cycle time has to be less than 500 picoseconds, right? Well, for the cycle time to be less than 500, these two have to add up to less than 500, right? Well, if that's 160, the biggest this can be is 340. So the 340 is random, but based on this. Yeah, so if, for example, instead the circuit had a total delay through it of 370 picoseconds, then this value over here would be 130. Because 500 minus 370 is 130. Okay. Now, I know, like I mentioned earlier, that you don't need to know the orientation of the skew for this. You just need to know what the worst possible case is. But it is important to know the orientation of the skew, because you could very easily be given a question where you're shown the orientation of the skew, and then you're expected to figure out which format of the equation you're supposed to be using, whether or not it's adding or subtracting the skew. So you need to be able to go from the orientation to the equations, or to the formulas. All right. Any other questions? Okay,
So
yep.
wait, just to clarify, because yeah, this is kind of confusing me. So when we have, I believe the buffer, it's showing it 2 to 1, like it's going in the direction from 2 to 1.
Yeah, so 2 is earlier.
So 2 is earlier. Okay, so that means then 1 will skew, and we add t skew to. Oh gosh, this is so like
Yep.
confusing.
It is. No, it is. It is.
So this would be the opposite of the picture you drew to the right, where 2 is earlier. So then we would add skew to the right hand side.
That's
Okay.
correct. Yes. Yep.
Yeah. Okay. This is going to take a few times for
It
me
is.
to like process it.
So I went through the derivation,
Yeah.
but I'm going to write kind of like the shortcut for it. So if it's skewed to the right, and when I say to the right, I mean if you're looking at this diagram, so your input register comes earlier than your output register. So if it's skewed to the right, then that means you subtract from both. And if it's skewed to the left, that means you add both. So if clock 2 arrives earlier than clock 1, that means you do addition on the right-hand side. So that's kind of the shortcut way to remembering it. Skewed right, you subtract from the right-hand sides. If you're skewed left, you add to the right-hand side of your equations. So if you want to remember it that way, like for tests and stuff, that's probably like the easiest it's going to get in terms of just raw memorization. But like I mentioned, it is important to know how we came upon these formulas.
That is super helpful, because we do have a test coming up, and
Yeah,
I will.
exactly. Yes. Okay, so with that out of the way, it should be relatively easy now that we've gone over this part for you guys to plug in whatever value it was you guys got from part A for this total sum. Do 500 minus that to get the skew, and then that's your answer for part B.
So it would just be t skew equals rows.
Yeah. Yep. So t skew in this case, the maximum t skew, so the most skew we can tolerate. It's going to be 500 minus whatever you got. Whatever you got from part A.
Sit down in the textbook and try to figure this out.
Okay. So with that in mind, what is the next part? What does the next part ask us to do?
How much clock skew can the circuit tolerate before it might experience a hold time violation?
All right, cool. Thank you. So we just talked about the worst case scenario for clock time, which would be skewed to the right or to the left. What's the worst case when it's skewed right or left for clock time?
To the left.
To the left, yeah. Using my cheat sheet chart, left means we
Exactly.
add. Adding on the right-hand side for the clock skew for the clock time is bad because we're making our period longer, frequency shorter, so we can't run it as fast. So to the left is the worst case for this. But we just talked about how it's always the opposite. It's the best case for the hold time going to the left. So if we want the worst case for the hold time, instead of going left, we're going to go right. So the clock is skewed to the right, which means that we subtract from both our terms. And remember, this is the worst case because we want t-hold to be less than this side. At the base, we have TCCQ plus TCD, but if we're then subtracting a number, now it makes it harder for this hold time to be small, or to be smaller than the right-hand side. So that is the worst case scenario. And so now we do a very similar calculation. We had some value of TCCQ plus TCD from the text, whatever it was you calculated. So I'm just going to throw out a number, and I'll say it was 30 picoseconds. And I'll throw out another number and say that the hold time, again, this would be in the text. Let's say it was 15 picoseconds. All that would mean is that my skew can be a maximum of 15 picoseconds. And the reason why is because if we do 30 minus 15, we get 15. 15 and 15 are the same. 15 is equal to 15, so that's as far as you can go. You can go less skew. You could go 14 picoseconds, because 30 minus 14 is 16, and 15 is definitely less than 16. But you can't go any further. So if you went to 20 picoseconds, 30 minus 20 is 10, and 15 is not less than 10. And so it wouldn't work out. So again, with the values you got from, or with the values you have given to you, you can plug it in here, figure out what this value is, and then you can figure out what your maximum skew time is just by subtracting these two numbers. Okay, so any questions about the hold time constraint? Okay, I'll let you guys go ahead and write down whatever work it is you have for about a minute. I'm going to pull up the next question from the textbook.
Can I also ask you a quick question about the wording on 3.33 Part D?
Yeah.
So just so I'm understanding what they're asking, or I don't know if you see it in front of you.
Yeah, I have.
Okay. My question is, when it says, what is her circuit? Do they just mean redraw it with?
Yeah,
it says
it's like a little story. She's like, oh, I can design a better circuit than this. So we're asking you, okay, what's the circuit she's talking about? The better
Okay,
circuit.
so just that's the drawing part. Okay, got it.
Yep. Okay, so I have the question 3.31 pulled up, so I'm going to actually fill in the values from here so we can get the correct values rather than just the example ones that I was using. So for the clock time, TPCQ, let's take a look. TPCQ is hold time, clock to Q, maximum, clock to Q, minimum. TPCQ is 50 picoseconds. The longest delay through this is going through 3 XOR gates. Each one has a maximum delay of 100 picoseconds, so the total is 300. And then the setup time in the problem is given to us as 60 picoseconds. And so this number is actually pretty close. It's 410 for the total delay here, 410 picoseconds. And so what does that mean our maximum skew can be? Assuming that we can't go any further above 500 picoseconds. What's the most skew we can tolerate? No need to be shy.
Wait, did you say 410? Wouldn't it be 430? Isn't it 70 plus 300 plus 60? Let me see.
I think 70 is the. Oh wait, yes. Thank you.
Yeah. Yeah, so the TCCQ is
Thank you. I
50.
read the wrong one. That's the
Okay.
contamination delay. Thank you.
Just making sure.
All right. Very similar,
So
but
then-
with 430. So what's the skew?
70.
70, exactly.
Yeah.
All right. Thank you for catching me on that. So now the next one for the hold time, very similar. So TCCQ here, that's the 50 picoseconds. And TCD, and that's going to be the fastest path through our circuit. So that's just following along this bottom line through one XOR gate, and the contamination delay of one XOR gate is 55 picoseconds. So that'd be 105 in total. And our hold time is given to us as 20 picoseconds. And so that means that 20 has to be less than the right-hand side. 20 has to be less than 105 minus the skew. So what can the biggest skew be in order for this to be still true? Well, I guess I'll ask first. Did I write down the same numbers you guys had?
Yes.
Okay, cool. So yeah, what's the most skew we can tolerate before this inequality is violated? That should be close. I think it's 85. Because when you add these up, you get 105 minus 20. It should be 85. All right. So now here's what we've discovered. If we have a clock skew to the right, so clock 1 comes earlier than clock 2, the most we can handle is 85 picoseconds of skew. And if there's a skew to the left, so clock 2 is earlier than clock 1, the most we can tolerate is 70 picoseconds. So we kind of have a range depending on what orientation our skew is in. No matter which orientation, as long as it's less than or equal to 70 picoseconds, we're good. And if it happens to be skewed to the right, we can go up to a maximum of 85 picoseconds. Okay. Any questions on that?
I think my only question is, we're looking for the worst case in both T-hold and the TC because of the wording, like how much can it tolerate?
Yes.
Or
Yeah,
Okay.
exactly. So let's say in the first example, we said the skew was to the left because that was the worst case. But let's assume that it was actually to the right. Well, if it was to the right, that would make this be able to handle longer and longer and longer times. And so all that means is that there's no bound on how fast we can run the circuit. So instead of having some upper bound, now we have no upper bound, and we can increase the frequency as much as we want without bound. And so if you did the problem incorrectly and then tried to do that, you'd realize, well, shoot, I can just keep increasing the circuit frequency if my skew keeps going higher and higher and higher. And so then you realize, well, shoot, that's the best case scenario. If I have lots and lots of skew, I can have my circuit operate faster and faster frequencies. Whereas if you have it the worst case scenario, then you actually have some sort of bound. So that's how you would, if you made a mistake, that's how you would end up figuring out on the spot. You'd say, oh shoot, I've just realized that I can keep increasing my frequency without bound.
Someone would
Okay, thank you.
problem, and have to know it for the exams. How important is knowing skew when it comes to design hardware?
That's an excellent question, yeah. To answer your question, unbelievably important. It is very important in your designs. Because you need things to be synchronized when you're doing calculations and when you're sending outputs to other systems. In order for things to be synchronized, you need to minimize your clock skew as much as is humanly possible. Because if you can't minimize it, then everything's desynchronized and nothing is running at the same time. So it just, in general, you want minimum clock skew as possible. What more can I say about that?
So whenever it comes to these flip-flops, we always have to consider the skew when designing.
Yeah, so there's some like inbuilt numbers like setup and hold time that are just unique to the registers you're using. So it depends on what the so registers are made from gates, and the gates are made from transistors, and the transistors are manufactured on a specific fabrication process. So you guys might have heard of like the 5 nanometer Intel node or the 4 nanometer node. That's just, well, the 4 nanometer, 5 nanometer, that's just a name. But depending on how they design transistors on those fabrications, that impacts those timing properties. So it might change the hold time, it might change the setup time. And so those are just numbers you'd get on a data sheet depending on the registers you're using. And then from those numbers, you would then do this analysis. But as I've mentioned before, we leave a lot of the design work to synthesis tools. I mentioned this before when it came to optimizing combinational logic. So, reducing the gates. Typically, if it comes to something with like more than 5 inputs, we don't really care enough to actually do it by hand. It's just unbelievably annoying to do. And we also don't do that, in industry either. You have synthesis tools, figure out what the best optimal configuration of gates is. And it's the same thing for hold time and setup time constraints. On Quartus, you might do this in CP, I'm pretty sure you do this in 300. You might do this in 200, I don't think so though. In Quartus, there's actual timing software that, given your circuit and given some baseline registers that they're using with specific timings, they can calculate what your maximum operating frequency is and what your minimum period is and what your hold time constraints are and things like that. And then from there you can say, okay, this is the most skew I can tolerate in this direction, this is the most skew I can tolerate in the other direction. So it's very important, but we typically don't do these kinds of hand calculations ourselves because the logic is just really complicated and there's a lot going on. So we leave that to synthesis tools, but it is important to know why it's even doing it in the first place. Why do we care about this? Well, if our skew times are off, our circuit's not going to work. And even if there's a little bit of skew, we could have bad timings and we could have registers receiving values at different times and nothing's synchronized. So it's an important concept handled largely in part by synthesis tools. Okay, so on to the last part of this problem, where it asks you guys to redesign the circuit such that it's better in the sense that it has better tolerance to skew, and it also can run at a higher frequency. And, well, I already talked about this with Shauna last Friday because she came in to the office hours, but for the other two of you, I want you guys to think about, at least for a little bit, what the redesign of the schematic would be, such that it implements the same functionality. You're still XORing 4 inputs. However, it's better in terms of timing. So I'll let you think about that for a little bit.
It still has to use a 2-input XOR, right?
Yeah, just for simplicity's sake, your redesign is going to just be using 2-input XOR gates, yes.
Okay.
And to give you a little hint, you're going to be using the same number of gates. You're still going to have 3 XOR gates. It's just the interconnections might be different. And then after you guys are done with this, I'm going to have you all think about parts B and C for the next problem, 34, because they're actually identical to what we just did for 33, just with a different circuit. So it's identical calculations, just slightly different numbers. And I'll let you guys handle that. And then if you have questions, you can ask me. But for now, has anyone thought of another way to wire up the XOR gates? Maybe not even just a better way, just another way, if that helps. As another hint, recall that when you're doing any operation like ORing or ANDing or even XOR, the order that you do the terms doesn't matter. Which is to say that if I swapped A and B at the inputs of this XOR gate, the result is still the same. It's still A XOR B. The order doesn't matter. Just like adding in math. If you do 1 plus 2, that's the same thing as 2 plus 1. The order doesn't matter. So I'm going to go ahead and draw that schematic. So all I'm going to do is I'm going to realize that here, while they're chained one after another, it kind of sucks for the maximum possible time delay because I'm going through 3 XOR gates. So to fix that, here's what I'm going to do. Bless you. I'm going to take this XOR gate and kind of slide it back. You'll see what I mean. So I took that third XOR gate and I'm going to move it back. So instead of being the third one in the chain, it's going to be receiving the inputs from C and D. So you're XORing A and B, and you're XORing C and D kind of separately. Or, to use a fancier term, in parallel. And then you feed the output of this XOR gate and the output of the top one to the same one on the output.
I just wasn't sure if that was even.
Well, yeah, let's analyze it. So now, let's think about the shortest path, the longest path through it. The one that takes the most time. So the one that takes the most time, well, actually they're all the same, right? Every single path is exactly identical. They all have a gate delay of 2. Before, how many gate delays was the maximum path? It was 3. So we've saved out on an extra 100 picoseconds of time, which means we can decrease our period by 100 picoseconds. So that's a lot better for our clock frequencies. Awesome. And we can also think about the hold time constraint and how we've benefited that. So the hold time constraint, you want the shortest possible path to be longer. You want it to take more time. Because the more time that the shortest possible path is, the more likely that your hold time is smaller than it. So the bigger this is, the better it is for your hold time. Before, our shortest possible path went through 1 XOR gate. But now, what is our shortest possible path? 2 XOR gates. So the change for this is, well, the TCCQ is the same. TCD, though, the shortest possible path is not 55 picoseconds. It's double that, because there's 2 gates. So it's 110 instead. And so what that means, because this right-hand side's bigger, it's a lot easier for the hold time to be smaller than it. So you can have a bunch of skew, and it'll still be fine. So that's why this circuit is a lot better in terms of both your clock time and your hold time violations. the longest possible path has been shortened, and the shortest possible path has been elongated. And so you can generally think of you can kind of think of the following diagram. So here, 0 and infinity just represent just times. So it takes you no time, literally 0 time, to propagate through your logic versus an infinite amount of time. What you want is you want this whole thing to be skewed to the left. So you want to take less time for stuff to go through your circuit. So that's about your clock times. But you also want your minimum time to be closer to infinity, because what that means is that you have best for your hold. So in general, you want this moved down, but you want this kind of range to be equalized. So everything has almost the same delay through the logic. So it's nice to have these two closer together. There isn't a lot of variation in your timings. There's consistency. And it's also nice to have it further down so that you can actually run your circuit at higher frequencies. Okay. Any questions for me?
When does a T-hole happen again on the register?
When does T-hold happen? So,
Or when, I guess,
like in the diagram, where it occurs? Yeah, so T-hold corresponds to the following. So, let's say you have the clock strikes. Now, what you had before is you had your signal propagate through the logic, and then it was waiting here. It was waiting here at the input of the register, waiting to be read in. That's the setup time. Now, there's also a time after the clock edge, which you have to have that signal steady as well in order for it to read in properly. That's the hold time.
and that's before we hit the next register
What do you mean before you hit the next register?
for the T-hole, because we have to hold it a steady signal.
Yeah, so what I'm saying is you have one register and it's outputting something. It's going through some logic, and then the second register is reading it in. So you can think of it kind of like this. On this clock edge, this guy outputs something. Goes through the logic, so it reads out of the register, goes through the logic, and then for this time, that's the setup, that during that time duration, you have a signal just sitting here waiting. It hasn't changed because after the logic propagated through this wire is now being held steady because this has not changed yet. So right now, for that T setup amount of time, this wire is holding the bit value 1 or whatever it is, and you want it to stay at 1. And then for this amount of time after the clock switches, now this register is outputting a different value on this wire. So now it's setting it to 0, say. Well, it takes time for that signal to propagate through. And we don't want it to propagate fast enough to come in before the hold time is over. So that's what the hold time corresponds to. If this went really fast, then it would come in before the hold time was over, and maybe the register would read in the wrong value.
So we want the hold time to be long enough for the next
We want it to be
register.
short. The hold time to be short. Because, let's say, oh man, I'll just point. Let's say that this is when the next value speeds through your circuit, and this is when it gets to the wire. Now the wire's changed, but we just said that we need it to be steady for this entire time, but it changed here. So now the register just read in the wrong value. What if T-hold was shorter? What if it went to here instead? I haven't moved my finger. Well, the logic propagates through as fast as it can, and it finishes here. But we're good, because what we just said was it has to be steady up until here. After that, it can change. We don't care. So the shorter the hold time is, the better.
If I could just
self-study.
It's a good idea. Okay. Any other questions for me? All right. So, like I mentioned already, problems from exercise 3.34, B and C, are exactly the same as what we just did for B and C of 3.31. It's identical. So I'll let you guys go ahead and go through those on your own. I don't want to go through them. And you can, if you want, tomorrow for office hours, if you're still confused about them, we can go over them again. But for the last 7 minutes, if you guys have any conceptual questions, or we can start talking about the system Verilog for question 3. I'm happy to do either. So
I have a vote for the system Verilog, but I don't know how everybody else feels.
System Verilog? Okay, we can do that. So I think what I'll do is I'll go ahead and share my screen. I'm going to have just a text editor out, so I'll do text editor. And I'll swap my recording software to show that. Notepad. Okay. All right, cool. Sorry about that. You won't be able to see the changes that I've been making, but they will in the recording, and I'll go ahead and share my screen. I think you guys... let me share my screen here on Notepad. Okay, cool. So I know you guys can see my screen as well as Notepad down there, but I have it as a separate tab. So what was your question that you had for the system Verilog stuff? Did I not hear? Can you guys hear me?
I can hear you, yeah.
Yeah, I just don't have it in front of me.
Okay, no, you're good. No worries. So the system Verilog stuff, was there a particular, do you remember if you had a particular part of that question that was troubling you, or do you want me to just talk about them?
General.
General stuff? Okay. So I guess I'll look at that first one. So the first one says that we need to name a module that has an output, a 12-bit signal output called Y. And we have an input signal A, and all that we're doing is we're doing a shift of the bits, and we're doing a sign extension. So, for example, if we had our input signal A as 0, 1, 1, so remember that in binary, that's 3. What we want Y to be is we want Y to be the same thing as A, except we want it to be shifted over to the left by 2 bits. So 0, 1, 1, 0, 0. So we shifted in 2 bits to the right. And then the next thing we're doing is we're going to sign extend the most significant bit of A up till we get 12 bits. So we have 0, 0, 0, 0, 0, 0, 0. I think that's 7. And so if we count these, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12 bits. And so the operation that we want this module to do is exactly what I've just done physically here. We start with this as the input, and we expect this to be the output, kind of like as a black box thing. So I'll go ahead and start writing out the module for this. So we want to name it getVal. And we have a few things. We have an input signal, so input logic, A, and this is supposed to be a 3-bit signal, so I put 2 to 0. And then we have an output signal. And that output signal is called Y, and it's supposed to be 12 bits, so I put 11 to 0. That's the end of my declarations for my modules. And so now I have to actually write the internals that makes this stuff happen. So the first thing I'm going to do is I'm going to talk about how to basically shift in bits. So to shift in bits, essentially the operation you're doing is you're just taking 2 wires and running them along with those other wires. So literally, if you physically think of your 3 A wires, all you have to do to shift it right twice is to put 2 more wires next to it. And now you read it like that. Now if you read the bits, you have 0, 0, and then you have the bits from A, 0, 1, 1. So the way you can write that down or notate that is with the concatenation operator. So if you have whatever A is, and you want to shift in 2 bits to the right of it, then what you would do is you would say 2 bits of binary 0. And this expression represents the following. That will represent 1, 0, 1, 1, 0, 0. Where this is what A is. So that's this one. Oops. So that's this one down here. And then those 2 zeros are what we shifted over by, because it asked us to shift left, and when you shift left, you fill in the rightmost bits with zeros. Now the next thing that we're asked to do is to sign extend. So sign extend is slightly more complicated than just shifting, because it depends on what this bit is, because that's the most significant bit for A. So we have to extend a 0 to all of the bits. But if it was a 1, we'd have to extend a 1 to all of the bits. Or in general, what we're extending to all of those topmost bits is the topmost bit of A, which I would label as A bracket 2. That's bit 2 of A. So remember that bit 1 of A, that's this least significant, bit 0 of A, that's this least significant bit, which is 1. Bit 1 of A is this middle one, and bit 2 of A is this topmost one. That's why it's labeled 2:0. The rightmost bit is bit 0, and the leftmost bit is bit 2. Same thing for Y. The rightmost bit is bit 0, and the leftmost bit is 11. So what you're doing is you're taking A2 and you're copying it into 7 more bits, because you have to sign extend it to 12 total bits. Here we have 5 bits, so you need 7 more. So you need to copy A2 7 times. The way we notate this is as follows. So I have 2 of these concatenations, and I would write 7, and then on here I would put a 0. And so what that does is A2. So this is saying you're going to take A2, and you're going to concatenate it 7 times. So you're going to have 7 copies of that same thing. If you decided that you were having a bad day and you didn't like yourself, you could instead write it out 7 times like this. A2, 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 A2. That's fine. You can totally do that. However, for those of us who do not want to have a bad time, instead we can just do it like this. So again, this concatenates that top bit, the most significant bit, 7 times, puts it on the leftmost 7 bits, and then it puts A, so 0, 1, 1, and then it puts the bottom bits as 2 bits of 0, just because you're shifting it over right. So this would be the expression we're trying to use, and all we would have to do now is assign the value, this expression, to the wires of Y. So all we're saying is Y is just going to carry those values. So if we think of literal wires, Y is going to be two wires that have ground on them, 2 wires that are the value 0, and then next to those 2 wires are going to be the 3 wires we got from A. And then that top wire from A, you're going to have it split into 7 more wires that come out that are going to be the most significant bits of Y. That's how you can physically think about it. But that's pretty much it for this particular question. So I'm assuming that the reason why she's going over this with you guys is so you learn about 2 things: the concatenation operator to smush bits together or tie wires together in in a multi-wire fashion, also called a bus. Whenever you have multiple wires, it's called a bus. So she's teaching you about that. And then the second thing is I forget what this is called. I think it's the repetition operator. But when you repeat something multiple times, you have that number on the outside, and then you have the curly braces surrounding the whatever it is you're trying to copy. What else? Oh, sorry, I made a mistake here. Got to have those extra colons on the outside of that. Okay, cool. But yeah, that's pretty much it for that first part of the problem. Does anyone have any questions for anything I've topped up or anything I've talked about?
What do you mean by the top of the
When I said top, I should have said most significant bit. That's what I meant. MSB. So the top of A, or rather the most significant bit more accurately, is the 0. Okay. Any other questions for me? All right. So since there aren't any more questions, I'm going to go ahead and end office hours. Tomorrow, same time tomorrow, because I know you guys' homework is due tomorrow, right? So I'll be here same time tomorrow. So if you have any other questions regarding this or any of the stuff we covered earlier, feel free to come on in and we can talk about it. But thank you guys for coming in. I'm going to go ahead and end the recording and stop streaming.
Thank you so much. See you tomorrow.
Yeah, of course. You have a good one.
Thank you very much.
You're very welcome.